Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing a structure of fructose and also I discussed a structure of glucose. Now I am going to discuss disaccharides. Disaccharides. We know that disaccharides on hydrolysis with dilute acid or enzyme yield two molecules of either the same or different monosaccharides. Again you listen, disaccharides on hydrolysis with dilute acids or enzymes yield two molecules of either the same or different monosaccharides. The two monosaccharides are joined together by an oxide linkage formed by the loss of a water molecule. Such a linkage between two monosaccharides units through oxygen atom is called glycosidic linkage. Question is asked. Again you listen. The two monosaccharides are joined together by an oxide linkage formed by the loss of water molecules. Such a linkage between two monosaccharides through oxygen atom is called glycosidic linkage. Means two monosaccharides unit will join to each other by a linkage. That linkage is called glycosidic linkage. First example I am telling you of sucrose. I will give two examples, first of sucrose and second of maltose. Okay. First, understand the sucrose. One of the common disaccharides is sucrose. Sucrose is the example of disaccharides. This is the common example. Common disaccharide is sucrose, which on hydrolysis gives equimolar mixture of D plus glucose and D minus fructose. Correct? Both are in D configuration. D glucose, then glucose is positive, means dextrorotatory, and D minus fructose means liporotatory. Left side it will rotate, and D plus means it will rotate in a right direction. Then now on hydrolysis gives equimolar mixture of D glucose and D fructose. Glucose is plus and fructose is minus. Then sucrose formula is chemical formula C12H22O11. This is the sucrose, common sugar what daily we are using in home. C12H22O11. This plus H2O means sucrose plus H2O. It gives C6H12O6. That is the D glucose. Plus again same formula C6H12O6. That is the fructose. Means sucrose on hydrolysis it gives one molecule of glucose, one molecule of fructose. These two monosaccharides are held together by a glycosidic linkage between carbon 1 of alpha glucose. Between carbon 1 there are total 6 carbon, but now I am talking about the carbon 1 of alpha glucose and carbon 2 of beta fructose. Last class I have discussed alpha and beta. Alpha glucose, beta glucose, alpha fructose, beta fructose. Last class I have discussed. Okay. Since the reducing group of glucose and fructose are involved in glycosidic bond, since the reducing group of glucose and fructose are involved in glycosidic bond formation, sucrose is a non-reducing sugar. Question is asked. Remember, sucrose is a non-reducing agent. Why it is non-reducing agent? Since the reducing group of glucose and fructose are involved in glycosidic bond formation, they are not free. That's why sucrose is non-reducing sugar. Then alpha D glucose, last class I told the formula, alpha D glucose ring structure, correct, ring structure. Then just that structure remember, alpha D glucose and other beta D fructose. You know that glucose and fructose differ only in the these things, H and OH. OH group is attached, then left side and right side, correct. Right side means glucose, correct, means alpha. Right side if OH is there, then it is a glucose, means alpha glucose, correct. Like that way, fructose in this alpha glucose right side and beta glucose left side. Like that way in fructose, same way. Then now alpha glucose and beta glucose, when they will come close to each other, then carbon number 1 and carbon number 1 of alpha glucose and carbon number 2 of beta fructose, okay, both will just their OH and H, they will actually both at carbon number 2 and at carbon number alpha means this glucose, alpha glucose, OH is there at carbon number 1 and beta fructose, there also at carbon number 2 OH group is there, means 2 OH group will come close. Then you know what will happen, both carbon number 2, carbon number 1 of alpha glucose and carbon number 2 of fructose, both have OH group. Then now these OH group will interact. Then OH and H, O and H, it will make H2O. Then only one O will remain. There are two OH plus OH. Then one OH plus one H. It will form water. It will go as a water. Then OH from the one carbon number 1, OH will go as negative. Then carbon will become positive and other carbon number 2 of fructose, it will lose H ion, H plus. Then that O will be negative. Then this negative O will join the positive carbon of glucose, alpha glucose at carbon number 1. Means carbon number 1 and carbon number 2, now both will be joined by oxygen. Then this linkage is called glycosidic linkage. Okay, glycosidic linkage means now carbon number 1 and carbon number 2 means alpha glucose carbon number 1 and beta fructose, D fructose, both are D. Then carbon number 2, now both are joined by O, oxygen atom, correct. Both carbon number 1 and carbon number 2 both are joined by oxygen atom, oxygen in the middle. correct? Then this is called glycosidic linkage, correct? Other arrangement is same, only OH only that is disturbed. H2O molecules went, and then this carbon number 1 and carbon number 2 both joined through oxygen. Then this is actually a structure of sucrose, that is the disaccharides. Sucrose is dextrorotatory, you remember. Sucrose is a dextrorotatory, means it will rotate the plane polarized light towards right direction. But after hydrolysis gives dextrorotatory glucose and laborotatory fructose. You remember, now this sucrose, when it will hydrolyze, then it will give 2 units, 1 unit of glucose, 1 unit of fructose. Then these 2 units, glucose and fructose, I am telling for that sucrose is dextrorotatory, but after hydrolysis gives dextrorotatory glucose. Glucose will be dextrorotatory, means plus, and fructose will be negative, that is the laborotatory. Okay, then on hydrolysis sucrose gives dextrorotatory glucose and laborotatory fructose. Since the laborotatory of fructose is minus 92.4 degree Celsius, degree only, this is the angle, okay, angle, minus 92.4 degree, correct? This is more than dextrorotatory of glucose. Glucose value is plus 52.5. Glucose, its value is 52.5 degree plus, and fructose minus 92.4. Then one is minus 92.4 and means fructose, and glucose is plus 52.5. The mixture is finally laborotatory, because fructose is minus 92 and glucose is plus 52. Then overall it will neutralize. Then finally the mixture will be laboratory. Question is asked, because fructose is minus 92.4 and glucose is plus 52.5. The mixture is finally, it will remain minus value only after cancelling. That's why the mixture is laboratory. Question is asked. Thus, hydrolysis of sucrose brings about a change in the sign of rotation from dextrorotatory, from dextro means positive to labo means negative, and the product is named as invert sugar. Correct? Remember, now product what will get? Mixture. That is the invert sugar. Again you listen. Hydrolysis of sucrose brings about a change in the sign of rotation from dextro to labo, and the product is named as invert sugar. Okay. This I have told you about the disaccharides. Correct? Means sucrose on hydrolysis brings about a change in the sign of rotation from dextrorotatory to labo, and the product is named as invert sugar. Now come to the maltose. Maltose, it is also disaccharides. Okay. Another disaccharide, maltose, is composed of 2 alpha D glucose unit. Now here you will get 2 alpha D glucose units, in which carbon 1 of one glucose is linked to carbon 4 of another glucose. In second unit, 2 unit will be there. Then in first unit, at carbon 1, and in second unit carbon 4 means carbon 1 and carbon 4 will join, correct. The free aldehyde group can be produced at C1 of second glucose in solution, and it shows reducing properties because aldehyde group is there, it is a free, that's why it is reducing sugar, correct. Aldehyde is free. The free aldehyde group can be produced at carbon C1 of second glucose. 2 glucose unit will be there. Then this at carbon 1 aldehyde group will be there. That's why this will be reducing sugar. The free aldehyde group can be produced at C1 of second glucose in solution, and it shows reducing properties. So it is a reducing sugar. Then again here this linkage is same linkage, that is the glycosidic linkage. Now here you will take both alpha D glucose, 2 units are there. Then when both unit will come close, unit 1, unit 2 unit glucose is there, both side alpha D. Then carbon number 1 and carbon number 4. Again both carbon OH group is there. Then again H2O will go and O will join the carbon 1. OH of first unit OH and fourth carbon, second unit fourth carbon. That both are OH. Then first unit carbon 1 OH, that will go as OH minus, then carbon will become positive, and fourth carbon of the second glucose, from there H will go as H plus, then O will become negative. This O negative will join the positive carbon of glucose first unit at carbon 1. At carbon 1, that carbon and oxygen, that is a negative charge, both will join. Then again it will form a glycosidic linkage. Okay. Then this is called, when both unit are glucose and linkage is a this glycosidic linkage is there, carbon number 1 and carbon number 4, between carbon number and carbon number 4, both are joining through oxygen, correct. Then this is called maltose. This is the structure of a maltose, means alpha D glucose 2 units are there, then both units are joined through oxygen at carbon number 1 and at carbon number 4. And actually question is asked about the sucrose and maltose, that linkage they will ask, where they are linking. Then sucrose, I told you that 1 and 2, carbon number 1 of first unit means alpha D glucose, and carbon number 2 of fructose, their fructose is there. Then 1 and 2, that carbon number 1 and carbon number 2 are joining with through O in sucrose, but here in maltose, carbon number 1 and carbon number 4 of alpha D glucose, 2 units are there, same unit, it is also joining, but through carbon 1 and carbon 4. This is the difference. Then this I told you about the structure of maltose. Now come to the structure of lactose. Third example of disaccharides. Lactose is found in milk, you remember. It is more commonly known as milk sugar. Lactose, third example I am telling you of disaccharides. Then lactose is more commonly known as milk sugar, since this disaccharide is found in milk. It is composed of beta D galactose. Here you remember, Here carbohydrate is in the form of beta D galactose, not glucose, not fructose, galactose, 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 and alpha D galactose and beta D glucose. Correct? One unit is galactose and other unit is glucose, but both are beta D. Both are beta D galactose and beta D glucose. Then here that beta D galactose, it is its formula is similar to glucose. Okay, here that again you can say that beta D galactose and beta D glucose both will come close. Then carbon number 1 and carbon number 4, again OH is there. OH is there. Then same way what will happen? H2O will go and both unit will join to each other through oxygen. Okay, then this is actually called lactose. Lactose has two units, beta D galactose and beta D glucose. Structure, now beta D galactose, I am telling you that carbon number 4, first to understand glucose, already you know beta D glucose, only structure is same, only position of OH is differing up and down, that's simple. Okay, then here that in galactose at carbon number 1, OH will be upside, H will be down, and in glucose OH will be down, H will be upside, opposite, correct? H will be upside, OH will be down, and in galactose OH will be upside and H will be down, correct? Hence again OH upside and OH upside at carbon 1 of galactose and OH down of glucose, both will interact, hence here also will get linkage, but it will be little diagonal because OH is upside, one OH is upside, other OH is down, correct? And so this time you will get again same linkage, but it will be diagonal. Okay, diagonal. Then this I have told you about the lactose. Now I will discuss about the polysaccharides. Then here examples of polysaccharides. What are the examples of polysaccharides? Then best example I am telling you, starch. Second example is cellulose. Third example is glycogen. Correct? Then actually all things you know, all things you have seen actually. As for example, I am telling you starch. Then in rice, starch is found. Water of rice, when you are cooking, you are getting that water, liquid you are getting. In that liquid, here you have now you have cooked the rice in water. Then after the cooking, you are getting the liquid, correct? Then that liquid actually, in that liquid starch is there. There starch is there, even in rice also starch is there, correct? Then this one example I am telling you, common example. Then one by one I will tell to all three. Then first you know about the polysaccharides. Already I have told you. Polysaccharides contain a large number of monosaccharides. Disaccharides only 2. And oligosaccharide, that maybe 2, maybe 3, more than 3, maximum 10. 2 to 10 units are present in oligosaccharides. Minimum 2, maximum 10. Maybe 4 also, 5 also, 6, 7, 8, 9 also. That is called oligosaccharide. But here I am discussing polysaccharides. Then here large number of monosaccharides units joined together by a glycosidic linkage. Already I have discussed what is the glycosidic linkage. These are the most commonly encountered carbohydrate in nature. Actually, these polysaccharides are common. Polysaccharides are the most common encountered carbohydrates in nature. They mainly act as the food storage or structural materials. Example is a starch. Starch is the main storage polysaccharides of plants. Correct? Here, starch is the main storage polysaccharides of plants. It is the most important dietary source of human beings. We eat daily this rice, okay, starch. Then starch is the most important dietary source for human being. High content of starch is found in cereals, even in wheat also. Roots, tubers are some vegetables. In vegetables also starch is available in high content. High content of starch is found in cereals, roots, tubers and some vegetables. It is a polymer of alpha glucose. Remember, it is a polymer of alpha glucose and consists of 2 components. Correct? It consists of 2 components. What are that 2 components? Then one is amylose, other is amylopectin. You remember, question is asked. This starch is made up of, or you can say it is consists of 2 components. First is amylose and second is amylopectin. Amylose is a water soluble component which constitutes about 15 to 20% starch. 15 to 20% starch you will get in amylose. Correct? Chemically, amylose is a long unbranched chain with 200 to 1000 alpha D glucose. Remember, long chain with 200 to 1000 alpha D glucose. It is made from the glucose units held by C1 and C4 glycosidic linkage. All rings are attached to each other. All units are attached to each other by a glycosidic linkage at C1 and C4. One unit C1 and other unit C4. C1 means carbon 1, C4 means carbon 4. Okay. And now come to the amylopectin. Amylopectin is insoluble in water. See the differences. Amylase is water soluble, but amylopectin is insoluble in water and constitutes about 80 to 85% starch, more than amylose. Correct? Question is asked. Okay, amylopectin has 80 to 85% of starch, but amylose how much? 15 to 20% starch. Now I am telling only about the amylopectin. Amylopectin is insoluble in water and constitutes about 80 to 85% starch. It is a branched chain polymer that was unbranched. Amylose was unbranched, but this is the branched. Amylopectin is a branched chain polymer of alpha D glucose units, in which chain is formed by C1-C4 glycosidic linkage. Here also bond will be formed between C1 and C4 glycosidic linkage. In both cases same. Amylose also, amylopectin also C1 and C4 glycosidic linkage. Only the difference is that amylose is a unbranched and amylopectin is a branched, and it is insoluble in water. Okay. This is the difference I have told you. Now I am telling you a structure of amylose. Then now you know it is very simple to tell the or write the structure. Suppose you have written 3 unit glucose you have taken. Then unit 1, unit 2, both will join at carbon 1 and carbon 4 through oxygen, and again second and third it will join same way at carbon 1, because first unit carbon 1 and second unit carbon 4 joined, correct, through oxygen linkage, glycosidic linkage. Then now carbon 1, unit 1 carbon 1 and unit 2 carbon 4, C1 and C4 has joined. Then now in second unit carbon 1 and third unit carbon 4, again it will join through oxygen glycosidic linkage. Like that way again 4 has joined of third, then first one is free, then that will join again with fourth unit. Third unit, fourth carbon is engaged, now first is free, then now this first will join with the fourth unit. Again 4, because fourth unit, fourth carbon will join, then again first unit of fourth will be remaining. Like that way it will join with 5th, 6th, 7th, like that way. Then long chain you will get, long chain, and long chain of glucose you will get. Okay. And now these things, amylopectin, then here actually I told you that linkage was alpha linkage. Here glycosidic linkage is alpha. Remember, alpha. Now amylose I told you. Now come to the amylopectin. Then I told you it is a branched. Then here now that this 2 unit you consider upside and 3 unit you consider down. Correct? 2 unit you consider upside and 3 unit you consider down. Then now 2 unit upside and 3 unit down, both will again it will make a link by glycosidic linkage. That is also called alpha link only. Then again same way here in amylopectin I told you, suppose you consider 2 are upside and 3 are down, then carbon number 1 in amylopectin that this up and down, suppose up I told you 2 and down 3 rings are there, correct? Then now both will join. Then which carbon they will join? Which carbon? Then it will join at means branching I am talking about, not the straight chain. A straight chain will be only C1-4 in both cases. In case of amylose, in case of amylopectin. In both cases there is a C1-C4, a straight chain. But these two straight chains are now joining to each other. That is actually at carbon C1 and C6. Branching occurs by C1 and C6 glycosidic linkage. That is also called alpha link. Then now carbon number 1 and carbon number 6. Then very easy, you can understand that in each glucose, carbon with carbon number 5, one CH2OH group is there. Already you know. Carbon number 5, ring you are considering, the out of the ring CH2OH is there. That carbon is the 6th carbon. Then from that carbon and this things, first carbon of glucose, both will join. Correct? Then first carbon H and OH is there in glucose. Then that OH, again same way, OH will go as OH minus, then first carbon will become positive, and CH2OH, from that only H will go. Then what will happen? Remaining will be negative, means oxygen will become negative. Correct? Because H is going as H positive, CH2OH. That H is going as H positive. Then O will be negative. Then this negative oxygen will join with the first carbon. Carbon 1 positive charge was there it will join. Correct? Hence there will be linkage between carbon and 6, and extra molecule will be formed as a H2O, because OH came from the this upper side. You have taken that this glucose was there, means upside that was there. This thing, linkage was there between two glucose. Correct? Then that will actually join with this thing, down three groups. I told you 3 units are joined. 2 units are joined to each other upside, and down 3 units are joined to each other by glycosidic linkage. Then now upside 2 and 3 side 3 units down. Now again both are joining through linkage, that is a glycosidic linkage. But carbon involved is carbon 1 and carbon 6. Then carbon 6 CH2OH was there, you remember. And this thing, carbon number 1 OH was there. Then H from the CH2OH, H gone, O become negative. This negative joined with positive carbon. At carbon 1, that is positive, it joined with that. Correct? This is called C1C6 linkage. C1C6 glycosidic linkage, also called alpha link. Correct? Then complete structure including all 5. Now all are joined to each other. All are joined through each other. Correct? Then now complete 5 ring. 5 ring is joined to each other. Then that is called amylopectin. Okay. Now same way you can understand by cellulose. Then where you will find the cellulose? Cellulose occurs exclusively in plants, and it is the most abundant organic substance in the plant kingdom. You will get cellulose just like bamboo trees. You have seen green. That is actually cellulose. Best example. Green means in plants it is found. Cellulose occurs exclusively in plants, and it is the most abundant organic substance in plant kingdom. It is a predominant constituent of a cell wall of a plant cell. In plant cell is there, then cell wall is there. How cell is made up of? Cell has a wall that is of actually cellulose. Cell wall of plant cell, it is found constituent of cell wall. There cellulose is found. Cellulose is a straight chain. Cellulose is a straight chain, but here it is a straight chain, but linkage is beta links. There in amylopectin there was alpha link. Whatever I discussed, all linkage, glycosidic linkage, that was the alpha link. Now here it will be beta link, beta. Then beta link means what? Beta link means here now you can say many unit will be of there of glucose. Then each glucose will join same way what it joined with alpha linkage, like same way it will join with beta. In the middle again glycosidic linkage will be there. Polysaccharides composed only of beta D glucose. There you have taken alpha D. Actually what I discussed till now, all were alpha D glucose you have used, but here you will use beta D glucose units. It is also glucose unit, but it is the beta D glucose, correct? And other what I discussed, that was alpha D. This is the difference, and bonding is same way, glycosidic linkage, correct? Polysaccharides composed only of beta D glucose units, which are joined by glycosidic linkage between C1 of one glucose unit and C4 of the next glucose unit. Same way, only in the place of alpha D glucose, now you have taken beta D glucose. That's enough. Here all glucose will be beta D, correct? And alpha D and beta D difference already I told you, that is of difference between the OH, whether it is a left side or right side. If right side, then alpha, correct? And left side beta, correct? Already I have discussed alpha and beta glucose, okay, no problem in that. Then here you remember in cellulose beta D glucose is used, and in a starch what is used? Either in a starch lactose, maltose and sucrose, what I discussed, everywhere alpha glucose you are using, alpha D glucose, but here you are using beta D glucose. Question is asked the differences, and now I told you. And branch differences, that here that is also C1 C4 linkage, glycosidic linkage, but it is of beta D glucose, okay. Now one example, last example I am telling you, that is of glycogen. This is also polysaccharides. Polysaccharides, third example I am telling now. First I told starch, second cellulose, and now I am telling you glycogen. Where is glycogen found? I will tell you, very important things. Glycogen, the carbohydrates are this glycogen carbohydrate I am talking about. The carbohydrates are stored in animal body as glycogen. It is also known as animal starch because its structure is similar to amylopectin. Its structure is similar to amylopectin, correct? Branch chain amylopectin, and is rather more highly branched. It is present in liver, muscle and brain. 3 places it will be available. First, it is available in liver, in body. Liver is there, in there liver will be there it will be a storage. In muscle it is a storage, muscle in our body, there also it will be there. In brain also it will be available, okay. When the body needs glucose, enzymes breaks the glycogen down to glucose, actually because it is a bigger unit, branched. When body requires glucose, Then this glycogen enzyme present in the body, like these things, many enzymes will be there, like diastase, okay, and these things, maltase. Many enzymes are there, diamase, maltase, and these are the enzymes actually. Then suitable enzyme, that in the presence of suitable enzyme, glycogen will provide glucose, correct, and it will go to the blood where it will be used. It will give a strength, okay. Then it is present in liver, muscle and brain. When the body needs glucose, enzymes breaks. Who will break? The enzyme breaks the glycogen into the glucose, okay, smaller, only in the form of glucose. Glycogen is branched, that will break into the glucose. Glycogen is also found in yeast and fungi, okay. And another places, glycogen is also found in yeast and fungi. Then whatever I discussed, all were carbohydrate in different name: monosaccharide, disaccharides, okay, oligosaccharides, polysaccharides. Then polysaccharides, this example I told you, starch, cellulose, glycogen. Question is asked, correct? Because sucrose is common, sucrose, maltose, it is common, but these are somewhat uncommon. Polysaccharides, starch, cellulose, glycogen. Then their structure it is asked, and linkage they will ask. Main is the linkage they will ask. What are the linkage? Correct? Then C1, C4 linkage is common, I have told you, and C1, C6, that is in a myelopectin, and again in cellulose, again C1, C4 only, but here beta D glucose units are used, correct? Then here in glycogen also you will find that alpha linkage will be there, but C1, C6 linkage will be there. Only this myelopectin is present in body. There it is called glycogen. Okay. And now I am stopping only here. Next class I will discuss importance of carbohydrates and other things. Thank you.